Second short video, this time we're going to have a little look, we're still looking at rotational motion, and this is, you need to watch both of these short videos really in order to fully understand what's going on, to be able to use what you know about a linear system and apply it to an angular system. So we're all familiar with a linear system, or should be by now, that uses SUVAT, where we've got linear displacement, initial velocity, final velocity, acceleration and time. We also use mass in linear systems. We can use one of Newton's laws, F equals mass times acceleration, when we're talking about linear systems, and also the energy equation for kinetic energy, K equals half mv squared. So you should all be familiar with that stuff, and this is designed to help you build on your knowledge of linear systems by extending those to an angular system. So these are sort of equivalents between the two systems. So instead of distance, linear distance, s in a linear system, we've now got an angle, angle of rotation, theta, in an angular system. Instead of an initial velocity, we've now got an initial angular velocity. So this is not the rate at which distance is changing, it's the rate at which the angle is changing in the rotational system. V, that's the final velocity. Omega 2, that is going to be the final angular velocity. We've got linear acceleration, we've got angular acceleration, which is the rate of change of angular velocity. We've got time, that's still time. Mass is used in linear systems. In angular systems, we've sort of covered this slightly or touched upon it previously in the last short video. That is the moment of inertia. And the moment of inertia is used in angular calculations rather than simple mass. So it comes in here, look, we've got force is mass times acceleration, and the sort of equivalent in a rotational system is T, and T is for torque, and torque is a force that tends to cause rotation. It's force times distance on a lever arm, if you like, if you remember that from other study. So we've got a torque, which is a force tending to cause a rotation, and that is equal to the moment of inertia, which is equivalent of the mass of the thing that's been rotated, multiplied by, this time not the linear velocity, linear acceleration, but the angular acceleration alpha. And likewise, when you look at energy calculations in a linear system, kinetic energy is half mv squared, while kinetic energy in a rotational system is a half I omega squared, where I is the moment of inertia, which is used instead of mass in these systems, and omega squared is the angular velocity as opposed to the linear velocity squared. Another thing you're going to need to be able to do is convert between revs per minute, which is a commonly quoted thing of rotating systems. It's the number of times something rotates in 60 seconds, in a minute. And we need to convert back and forth between omega, which is in radians per second, and RPM, which is in revolutions per minute. And that's quite straightforward. If you imagine you've got the RPM here, so that's a revolution per minute. If we divide that by 60, we get revolutions per second, and if we multiply that by 2 pi, which is the number of radians in one revolution, then we get the number of radians per second. So omega is RPM over 60 times 2 pi.